during my part of the presentation, I'm going to focus on general machine learning concepts. First of all, let me see, just a quick review of what is the difference between this nomenclature, right? What is AI that you can see in many papers out there, many magazines about computer science, or it's everywhere you read it. So what is the difference between AI and machine learning? What are the other tools, AI tools that are available? So to simplify, AI, it's a field of mathematics that has been there for quite a while, since 1956. And what they were trying to do, the goal was to mimic human intelligence to solve problems. So like, try to recognize some parts of speech, what, Siri or Alexa does, automatic translation, find the shortest path between two points in a graph or in a map. Those kind of things, those kind of problems have been there for quite a long time, and there were solutions for those problems before machine learning. There were statistical methods, probabilistic reasoning, typical mathematical optimization to solve particular problems, graph-oriented algorithms. So all that was there, and it's part of the AI. But then machine learning came when we started to, instead of approach the problem from a formula perspective or optimization perspective or analytical way, somebody thought, okay, why don't we build some way of actually learning what are the relationships inherently defined by the data? So the key difference in machine learning is that we are learning from data. We need a data set that we can learn from, or that we can analyze and extract patterns out of that. And that is the main difference. So through this, all that time, there has been an evolution, like starting from the global traditional approaches to artificial intelligence, then machine learning showed up, and then things continued evolving, especially lately on the neural networks field, which is with this, I'm sure that you have heard about deep learning, deep neural networks. That it's just an evolution, a new technique, or an evolution of neural networks, because at some point in the middle 70s, neural networks got stuck because we need a lot of computational problem to solve the problems that usually are solved by neural networks, like image analysis, speech recognition. At that point, things got stuck with neural networks until we got a huge leap with co-processors, and NVIDIA came up with GPUs. And then that provided the computational power to keep advancing the neural networks approach, and that is pretty much where deep learning showed up. So in Tuple, we are using multiple techniques to solve problems that we are very practical oriented. Most of the time, if the problem can be tackled with a classical machine learning approach, there is no need to get into the complexities of deep neural networks or more fancy or bleeding edge advanced algorithms. If you can get the work done with a simplest approach or a simpler approach, that is better, because it will take less time to train, it will be easier to tune, easier to understand what the algorithm is doing, etc., etc. So this is just a few list of some of the algorithms, machine learning algorithms that we are using. There is the two big families in machine learning. There is the supervised learning, which is learning from a labeled data set. What that means is that you need to provide the data set needs to provide examples of the problems that you want to solve. For instance, if you want to detect a drop call rate problem, so you have to provide examples of what a drop call rate is. So the engineer will collect that data set and will say, okay, this is an example of a drop call rate. So the data is this, these are the KPIs of this sample, and then you label it as a drop call rate, or you label it as a, I don't know, internet issue, or low throughput, or coverage problem. So you need, the label is the key. Then the algorithm will be able to read that data, go through that data. Different algorithms will process that data in a different way, and to learn what makes a sample to be a drop call rate problem or a coverage problem. So in the future, when new data is coming, the algorithm is able to say, hey, this is similar to what I saw during training of a drop call rate problem, or a coverage, or Hanover, or throughput, right? That is supervised. And supervised is a different way to approach, or we are trying to solve a different problem. We just have, you have data, and you don't need to have a label, because sometimes you don't even know the label, what the problem is. So you just use machine learning techniques to say, hey, this is my data set. I don't know what is this about. Just try to find a relationship between within this data, and then I will try and analyze. Once the relationship is discovered, I will take a look at it, and I will see if that is actually interesting from an engineering perspective. That is an example of clustering, or same thing, or a similar approach can be done for feature discovery, right? Like, I have a bunch of data, and I just want to find out what parts of all the different dimensions of the data are the most important. Or, yeah, because that is a key thing, because usually the data that we get has many different components, like hundreds of components, but not all of them provide quality information, so that the machine learning algorithm, the machine learning supervised algorithm, can learn from it. So usually it's a way to like simplify the initial data set and focused only on the data that is, on the parts of the data that is really providing enough info to learn from. Then in here, this is just like a way, or a quick way to navigate through the different steps or approaches that you can go when you have a data set. So you start with a raw data set. You can clean it, or you can just analyze it. Just, okay, what is this about? You just can visualize the data set based on what you see. You decide to clean some data, transform some other data. You can go to use this dimensionality reduction I mentioned before. And once your data is, pre-processed, then you can use it on the different depending on the problem that you want to solve. You can go and do clustering, or you can do classification, or you can, if you can do regression problems, work on those type of problems, and or you can get into deep learning for more complicated problems that you have. The main difference between classification and regression, those are two main categories within the supervised family of algorithms in machine learning, is in classification, what you are trying to predict is pretty much a class. It's just a type of problem. So problem like, is gonna rain? Yes or no? Is this a coverage problem? Yes or no? Is this a Hanover problem, or it's a throughput problem, or it's a Hanover problem? So it's a class, that what you're trying to predict. In regression, what you're trying to predict is the value of a actually something that you can measure. It's like a simplest way to put this is like a what is the throughput of a particular cell in the next couple of hours, right? Well, the throughput is going to be, I don't know, 2 megabits per second, something like that. It's quantifiable. Or how many subscribers I'm going to have in the next month. So it's something quantifiable. It's a number, right? That's the main difference between classification and regression. And with deep learning, you can do both. There are many different problems in classification problems that are pretty hard, and also regression issues that are pretty hard. Some people decided because they get stuck, they don't get the performance they want with a traditional approach, and then they decided to go further and start using more complex method like deep learning. In our case, for instance, we used deep learning, deep reinforcement learning for the RF shaping application. We were solving that problem using deep learning. And in general, as I mentioned before, traditional approaches are very useful. We should be very pragmatic and don't use technology for the sake of using technology. So if machine learning now is a big hype, everybody wants to use machine learning, but well, maybe machine learning for some problems that you have isn't the best way to do it, or not the simplest way. You will get good results without getting into the complexity of machine learning. So definitely, if there is a traditional method that you can use it. You don't need machine learning for everything. But there are also many situations and the systems that are very complicated. They start very simple, but then as time passes by, things get way more difficult to manage. And then you get to a situation where traditional approaches are not helping you. They are preventing you from making things faster and more efficiently. In those cases is where machine learning makes sense. For instance, some examples of that, when we have very complex patterns in our data. Traditional approaches like rule-based systems, expert systems in general, they can be used for that, but they rapidly become monsters of rules that are very difficult to manage. Rules get outdated. There is a lot of coupling between rules, and then you change one rule, then a bunch of other rules get affected by that change, and that becomes a nightmare in terms of maintenance. So with machine learning, you forget about that because everything is based on the data. So when the system gets more complicated, more complex, things get more complicated, that complexity, it's inside the data itself. So, and because you are learning from the data, then you just have to retrain your system to capture those new complexities. And another advantage of using machine learning is that systems are frequently changing, as I mentioned earlier. So because there are new patterns are showing up, old patterns have stopped happening. So that dynamic is way easier to capture when you just have to retrain your model. You don't have to change hard-coded rules based on what you are seeing in the network. It's just a matter of, okay, I just need and create a new data set based on production of what is happening in production and then retrain. And also there is some very interesting rule that happens very frequently in machine learning is that usually you can use simple algorithms as long as you have a lot of data. So simple algorithms with a lot of data to capture all the complexity of your systems is usually better than have a super complex algorithm, super advanced, that takes forever to train and then, but is based on less data. As a general rule, that is going to be more dangerous. That system is going to be more complicated to maintain. And then, of course, there are disadvantages of using machine learning. I tried to summarize in just 4 different blocks. First of all, is because we are learning from data, we need good data. If we don't have good data, then we can't learn patterns properly. And then once we have good data, we need to make sure that the training process is sound. There are many ways to train a data set, and there are, not, for instance, the fact that you have a book that explains very well how, fluid dynamics works. It's a complex topic, fluid dynamics, and you have the best book in the market, but you are not, you as a student don't understand, or you are not able to absorb that information properly. So you are not training yourself properly. There are many ways. You have to make sure that the training process is sound and that you understand, you are able to capture the patterns that are in the data set properly. Then it is a key aspect that sometimes is forgotten, and which is that you might have a very good model, good data, very well trained, but then the model is very well trained, and the predictions that you're getting from the model are pretty good. But then you don't understand how the model arrives to that conclusion. For some problems, that is good. That is, you don't care about that. For instance, Google, the image classification engine. You just want an engine that is able to detect humans within a picture. How the algorithm gets to detect the human face, you don't really care. You just know that it works, right? But for us, as telco engineers, it is always good to understand how the machine arrived to that conclusion. You need to understand, like, the thought process that led the algorithm to that prediction, and that is a key aspect of tuple system. When we provide a prediction, then the engineer has ways to analyze how, what was the data there, what was the definition of those features there. It's easy to explain and understand how the algorithm got to that conclusion, which is good because the engineer has a way to validate that the result is good or not. It's a good way for the engineer to say, hey, I think it should be this, but no, I understand why the algorithm gave that answer, and I kind of agree with that as well. It could be a way to solve that problem. And also, it's like a learning material for the engineer. The engineer can learn new stuff from the system. If the system is a black box, you get your input and then you get your output, and there's no way to know how did you get there, then the engineer doesn't learn anything. It's blindly relying on whatever the machine is saying, which is not a good idea in general. And finally, there is a key topic, I think it's very important, which is related with the quality of the data set. Because we are learning from the data, and in classification problems, we need labeled data. We need examples of what is a coverage issue, what is a drop call rate issue. So that label is set by an engineer based on the knowledge of the engineer. But as you know, we as engineers, we have different points of view, So I can say, okay, the main reason for this customer experiencing this bad quality of service is we have a coverage issue here. And then other engineer analyzes the same data and arrives to a different conclusion. Say, no, well, we have a coverage issue, but the real problem is that the terminal is very old and is not updated, the software is not updated, etc., etc. So it's very important that we train our model with a data set that has certain consensus, again, within the engineers that are going to use the system. Otherwise, the engineers will get, okay, it's telling me this, but the system is telling that the problem is this, but I don't think it is. But then the other engineers starts to argue why not, and those kind of things. So I think that this is something that usually we don't discuss, but is worth noting that is important for a machine learning system to work well.